Without a KV cache, every new token rebuilds attention for the entire prompt. Hugging Face Transformers lets us expose the stored keys and values and measure why generation speeds up. You'll trace KV cache reuse and compare cached versus uncached decoding latency across context links. I'm Professor Pi, teaching AI foundations with simple Python. Language models end up doing the same attention work again and again when you generate multiple tokens. That repeated work costs time and compute. A KV cache keeps the attention keys and values from prior tokens, so the model can reuse them instead of rebuilding the whole attention table. For interactive systems or long generations, reusing that cache state cuts latency and lets CPUs and GPUs spend cycles only on the new token. Think of attention as a lookup, how every prior token connects to the current one. Without a cache, you rebuild that whole lookup each step. With a cache, you only append the new row and column for the newest token. The code change is small, but as the prompt grows, that small change multiplies into real speed wins. We'll build a compact experiment. Inspect the cache shape. Verify reuse keeps outputs the same. Measure timing across prompt sizes. And implement a small manual loop that updates the cache step by step. The aim isn't to ship a server, it's to make KV caching concrete and measurable. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we load a tiny model and a tokenizer, so the experiment runs quickly on your machine. That keeps the cache state small and easy to inspect. This snippet loads the smallest useful Hugging Face Transformer setup for looking at a KV cache. We use AutoTokenizer.FromPretrained and AutoModelForCausalLM.FromPretrained with sshleifer TinyGPT-2, so the later experiments stay fast enough to run locally. The input is a tiny prompt, and IDs becomes the tokenized tensor the model will attend over. Starting small matters because KV cache behavior is easiest to see when the token count is obvious. The visible output confirms the prompt length and model family before we inspect cached attention state. Next, we run a forward pass and pull the model's stored attention state so you can inspect its shape and token axis. This example runs one Hugging Face Transformer's forward pass and pulls out out.past key values. Without caching, the model would rebuild the key and value tensors for these same prompt tokens again on the next step. The code handles both the newer cache object style and older tuple style, then reads the first layer's keys and values. The important axis is the token axis, where the cache length matches the prompt length. The visible output shows that the model stored reusable attention state for the tokens it already processed. Seeing the cache is useful, but we must prove it is safe. The next snippet compares logits produced by recomputing the full prefix versus reusing the cache for a single next step prediction. This code checks that Hugging Face Transformers can reuse cache without changing the next step result. The fresh path feeds full IDs back through the model with use cache false, so it recomputes the whole prefix. The cached path feeds only next ID, while passing past key values equals cache, and an attention mask covering the combined past and current length. If the cache is aligned correctly, both paths should produce effectively the same logits for the same context. The visible output shows the numerical gap and the chosen token, which makes cache reuse feel concrete instead of magical. Measuring correctness is one thing, measuring speed is another. The next snippet times generation with and without the cache across a range of prompt lengths, so you can see where the payoff appears. This snippet times the pain point directly with Hugging Face transformers generate. For each prompt length, bench runs generation once with useCache equals false, and once with useCache equals true. Then rows keeps the measured pairs. Longer contexts make repeated recomputation more expensive, so the best ratio often appears at the larger prompt sizes, though exact timings depend on hardware. Increasing max new tokens usually gives caching more chances to help, while decreasing it makes fixed overhead more visible. The visible output reports the context length where caching helped most, and the measured latency ratio. After we understand the numbers, we build a manual decoding loop that actually reuses and updates the cache step by step. This makes the pattern explicit and easy to adapt into custom servers. This example turns the cache idea into a minimal Hugging Face transformers decoding loop. Dynamic cache holds the growing key and value state, while cur is the full prompt only on the first step, and just the newest token afterward. After each model call, next ID is appended to IDs, and mask is extended, so attention covers both cached past tokens and the current token. That is the core reuse pattern. Keep the past in past key values, and send only the small new piece. The visible output shows a complete generated string from a manual cached baseline. If you map this toy loop into a real service, the same pattern holds. The server accepts a user prompt, runs the initial pass once, and then for each user turn or generated token, it sends only the new token plus the stored past key values. On larger models, the saved compute becomes bold, and on multi-user systems, it translates to higher throughput and lower cost. What this is, a concrete look at how KV caching stores attention keys and values so you do not recompute prior tokens. When to use it? For interactive generation, streaming outputs, or any long prefix where repeated decoding is expected. One caveat: cache alignment and attention masks must match exactly, or outputs will drift. A practical next step is to raise max new tokens and rerun the same timing sweep, or swap in a larger model such as GPT-2 Medium and compare the same prompt lengths to see how speedups scale with model size. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.